welcome back to the final topic of the whole course, which is where we go into the more general group setting. And we'll try to apply these ideas that we've done in the cyclic group of p elements in a more general finite group. So it can be actually any finite group. It doesn't have to be a billion on group or anything like that. And this idea really works there as well. And a lot of this does work in a very similar manner until we go into the notion of Fourier transform, but that comes in the later videos. So let me kind of begin the kind of process of what you need to do in the basic setting. So this is about the random walks on finite groups G. So that's the setting we want to consider here. And so what we have here is that we can do a lot of the kind of similar theory that we've done in the ZP. So let's first of all what the setting for us is. So we have a group, let G be a group, be a finite group. And let's assume that there is some group operation there, which I don't want to write. So I'm writing it in these terms of multiplicative operation. And then we let this xy in G for x in G and y in G be the group operation. So we have this. So I'm going to use this multiplicative operation. And then also what I have here is that we let 1 in G to be the identity element. So that means basically that if you take 1 of x from left or right, you get the value x for every x in G. So you can form this like the identity element inside the group, and what we have here. So this is the basic setting we want to do, and now we have to basically talk about the random walks in this group. So we need to talk about probability distribution. So we just recall that mu from G to 0, 1, a function, is a probability distribution if the sum over the elements in the group, x in the group, this is equal to 1. So that's the definition of a probability distribution in the group. A couple of basic examples are the uniform distribution, so lambda, which is the uniform distribution, which is 1 over the cardinality of the group of here, and then we also have the Dirac distribution at some point x, which is just given by the 1, 0. It's the same as we have done already inside here in the general setting. So so this is for any x in G, and this is some y in G. We define the Dirac mass. So this is called the uniform distribution. And this is called, I would call this the Dirac distribution. This is sometimes also, I call this sometimes Haar distribution, or Haar measure, or the Lebesgue distribution. Various ways to define this notion. But we have these like two kind of main examples that you typically have. And then if you have the Dirac distribution, we can define if mu is if you have a probability distribution from G to 0, 1, probability distribution, then this of course implies that we can write mu in this form as a sum with some maybe some numbers alpha x from G of the Dirac mass at the point x, maybe use the word y, maybe y. So you can write everything as a Dirac mass because it's a finite group. You can write them in this convex combination of these measures of the probability distributions. Okay, and in the same way as we did in the group ZP, we can also define that if A is a subset of G, then we can define mu A, the probability of this like event, as the summation of x in A, and here the mu is G01 probability distribution. Then we can define it as this sum. It's like we did in the group ZP. There's no change there, the probability, and then this allows us to define that if x is a random variable, or maybe let's call it like maybe z is a random variable in G, or maybe use big X, maybe that's the best. If big X is a random variable in G with the distribution mu, we mean that the probability of the random variable getting a value x is equal to the mu of x for every x in G. That's what we define, what we mean by a random variable with distribution mu. Then the probability of this event is positive. And so that, for example, if for every event A in G, we have that the x being in this event is the mu of A. So that's the kind of, now we can talk about the events and the probabilities of random variables using these probability distributions, like we did in the ZP. So now we can define, for example, the L1, maybe let's go to the total variation distance first. In G, so we can define it in the following way, that the total variation distance between two probability distributions is equal to the maximum of mu of A minus mu of A, where A is a subset of G. So that's the definition. We take all the possible subsets inside the group, so we can formally define this for any mu and nu G01, a probability distribution. Okay, all same. I'm just basically taking the ZP, I'm just replacing it by G everywhere, so that's what I'm basically doing. And then there is the L1 identity, which we prove in ZP, but the same proof for the any finite group, that if you want to compute the total variation distance, it's always a half of the sum in ZP, mu of x minus mu of x. That's the way it can be done in the general way. Okay, so the proof same as G equals ZP. So now, once you have this setting, we can now talk about, for example, if we want to compute events, we could then start to just compute these quantities. And we can then, in the same way, you could, like, for example, define the LP norm. So if you can define, like, if f is a LP norm of a function, we could then define this in the same way as summing over G of f x to the power p, 1 over p, or maybe I use this notation, 1 over p for any p between 0 and 1 and infinity. You can define this notion for LP norms in this way. So this implies that the total variation distance can be written as half of the LP norm of the universal 1. This is the L1 identity. And in the same way, we have, like, all the kind of things like where we could define as before. You could define the notion of convolution, for example. But here we get a little bit of an issue with the corresponding ZP, because ZP is an abelian group. So we have to like really be careful from which side do we convolve with. Like for example, when we are in the symmetric group and we are doing like modeling, like say card shuffling, for example, then it's really important to distinguish between which side of the group you are in. So that's why we have to define a right and left convolution. So let's take if f and g are functions from G to, let's say, complex plane, and then we define the left convolution is this quantity L of x at the point x. So you sum over the group y, and then you take the product from the left of y, g of y, and then the right convolution. This is all the points in G, and the right convolution is then the f star r g x. So you're taking it from the right instead. So this multiplication here from the inverse is now x y inverse here, g of y. X in G. So it's like you can think about it as you can take the from both way around, but it's give you like a different type of a evolution for the random walk. But typically it's like it doesn't exactly matter which one do you use in the actual theory, but the one that we are going to be using most of the time is going to be the right convolution. So from now on, we just use the right convolution. Which gives you that we define this convolution operator to be just the right convolution. When we write here convolution, let's say two functions, we mean exactly that this is just the y in G fx y inverse of gy. That's what one we are going to be using from now on. But this is really important because now you need to be careful if you are applying these convolution operators and you're doing like swapping here. You can't really swap these elements, for example. So you think about if you have a finite group, the finite group could be, for example, defined by matrices, for example, some finite group of matrices, if you could construct such an example. And there you might not be able to swap these sides, so you might not be able to get the same quantity as we had here. So okay, so that's the kind of a setting I want to talk about of the left and right convolutions. And now, in the same way, you can define the iterated convolutions. In the same way, so you could take the mu star n, let's say of a probability distribution. We define it just to be the mu star n minus 1 convolved with mu for any n at least 1, and then we here define mu star 0 to be just the Dirac mass at the identity element. Remember that 1 is the identity or the neutral element. So in the case of the group ZP, the identity element was the point 0 inside the group ZP if you use the additive group structure here. So here we are using this multiplicative notation. So that's why we have the Dirac point at the point 1. So that's the notion of iterated convolution. And now we can take the following, that if x1 and x2 up to xn are IID random variables in G, such that the distribution of each of them equals x is equal to the mu x for any x in G for some probability distribution mu, then this implies now that this xn, which is now defined to be, I could define it as the sum of these elements, so x1 x2 up to xn. So okay, here I'm multiplying from the, taking it from the right, but you could also define from the left if you wanted to use the other type of convolution. Then this this element now has a distribution probability mu star n, i.e. the probability of xn being equal to some x is equal to mu star n of x for any x in G. If I took this correctly now from the right to the convolution side, you should get this. I think, yeah. Okay. Just to make sure I did it correctly. Have the right amount. Yeah, that should be fine. Unless there's any mistake on the way we from which side we multiply. Okay, so now you have this notion of you can talk about now random walks on the group. So this is a random walk on G with the driving distribution mu. And now the kind of next time, so if you want to like really analyze this random walk, so we have now the notion. So if you want to like, for example, understand what is, for example, the probability of this xn being in A, like in a point A, and you want to subtract, for example, whether it's, let's say, close to the uniform distribution, then in the same way we could study this like quantity like what we had in the case of ZP, where this the cardinal of the group G was equal to P. Then we could study this distance. Then by the L1 identity, we can bound this from above by the half of the L1 norm of the mu star convolution n minus the uniform distribution and take its L1 norm. So that's the way we can always bound this distance for for any A in G and for any n in N. So in order to analyze then the random walk, how it behaves asymptotically, we need to then understand how this like distance to the uniform behaves in this way in the L1 identity. And for this purpose, when we could then use again, we could talk about the Cauchy-Schwarz inequality, and then hopefully use some notion of Fourier analysis in the group. We might be able to get an estimate for these probabilities of events in the group. And for that purpose, we need to talk about Fourier transform. So in order to do the same things we need in the case ZP, we need to define the notion of Fourier transform. Okay, so for the next time, I will start to talk about the notion of Fourier analysis a little bit, so I begin the notion of Fourier analysis in the general finite group. But in order to do that properly, we need to talk about the notion of representations in the group. So we will talk in next lecture on the kind of basic notions of representations in the finite group, and then use the representation theory to construct the Fourier transform in the group. And once we have constructed Fourier transform, the next topic is to prove a Plancherel's type theorem in the finite group G, which allows us to then prove the upper bound lemma, which we saw in the case of ZP, gives us very efficient estimates on, for example, the mixing time of the random walk. Like, for example, if we want to estimate this example, the probabilities of the random walks hitting some set A, then we just need to bound the kind of the rate of mixing of these random walks. We will see that it will be a much more complicated in general non-abelian groups like the symmetric group, but it's still possible to actually do these estimates, like in the case of card shuffling, which we see at the end of the course. Okay, so that's all for today, and thanks.